Legare. I'm here to present work done in collaboration with my colleagues at the NSS Lab at UBC in Vancouver, Robert Sumi and William Aiello, a platform for private web apps. So we have all these new privacy-enhancing applications that are coming out, offering cool things like end-to-end cryptography. And those things are great because users are finally getting the confidentiality they want from their service providers for applications, their ISPs, and their governments. But one question you might wonder whenever you encounter a new one is this app secure? Is it really private? And these applications are either malicious, or if they're not, they're vulnerable like any other application. And some of them might give you different privacy guarantees than the ones you'd expect. For instance, lately, it has surfaced that sharing links on Facebook private messages these links would be available publicly using their APIs. So we have all these applications. How would one user gain assurance in these applications? Well, you could audit the code. Tough luck with that. There's a lot of code. It's really difficult. If there is a public release of some software, you can hopefully rely on the conclusions of a diligent self-identified community of experts to tell you whether it's safe to use or not. But that's not always available. And for the web model, for instance, it doesn't work at all. The code you're served during one visit may not be the same that you get in a visit after that. And plus, even if you go all the way to do all that work, you'd have to do it again for the next app that comes along. So the problem with these applications is that the client-side code does everything. It has the private information, the keys, and without the containment of the keys, the plain text, and the crypto functionality, all of the application must be in a trusted computing base. Moreover, this has to be done for every application. So what you end up trusting in the case of web applications that enhance privacy is that you end up trusting all your browsers, the browser you use, the browser platform, and all of the applications are in one bucket. You have to trust everything. So we wanted to alleviate that problem with this platform we're introducing today to you, Beeswax. It's a security platform that will reduce the TCP of private web applications. What it does is it disaggregates and contains the security critical data and functionality from these applications into a platform, and it shares that common functionality between apps through well-defined APIs. And what this allows is that the experts can focus their scrutiny on the platform rather than doing it for every application. We have a prototype implementation implemented as a Google Chrome extension and about 5,000 lines of code. It's deployable now, and as we'll see with the eval, we've managed to do some cool applications with it. So this is a screenshot of ChatCrypt, which is a client-side secure chat messaging, so you can chat with your friends securely. And if you try to decompose this web application into various components, you'll see that this application calls into the browser runtime. It does crypto. It has logic to move things around. It passes ciphertext to the software, the service provider, and it has a UI so that it displays the plain text to the user. All of that stuff needs to be trusted because it does everything. And if you take a second application, well, the second application comes in and brings all of that stuff as well. So it reinvents the wheel, does everything again, and the only thing you have in common is the browser runtime that it gets reused across applications. So one thing that's bad is that if there's a vulnerability in any of these two applications, then you can exfiltrate the plain text of the data either to the application provider or another user. What we'd like to do with Beeswax is to not have to trust the application. We want a way where we just have to trust the platform, and all of the security features are taken care of by this platform. So what we notice first is that the keys need to be moved out. So what we do is we move the keys to the application platform. So we do all the crypto inside the platform, and what we give the application are key handles to these, so the application doesn't see the keys. Of course, that's not sufficient. You also need to take care of the plain text. So it's a web application. So You want the application to still manipulate ciphertext, but you want to let the user see the plain text, and that's a bit difficult. So what we do now with Beeswax is that we provide ways to view the plain text for the user without the application being able to see it. All the application sees is ciphertext. And the only way application developers are going to use the platform is if it's easy to use and if they can keep doing what they're doing, having a look and feel that's different for each application, and maintaining their development practices. So there's a lot going on under the hood. I'm not going to cover everything now, but I want to give you an overview of how it works. So imagine you have this application which lets a user talk to two friends securely. The way it would work in Beeswax is we define something called a private area. It's defined by the application. There's an API call, and the application says, I want the message of this, the message to be encrypted only for these two users. So I'm going to define this box. You pass the DOM element. It creates what's called a private area. And from that point on, the platform prevents the application from accessing the contents of that box with JavaScript or other methods. And the isolation technology we use is Shadow DOM. We have prototype overriding. We do content hiding with the JavaScript closures. There's a lot going on. And we also do something with the event system so that the user events are not leaked to the application when they pertain to this area. Right. Now, if the application wants to display something in there, what it has is ciphertext, and it passes the ciphertext to the API, to an API call, which displays it in the Beeswax controlled area. So the user can see it, but the app can't see the plain text. That's the way it works. So if we go back here, we have a way to isolate the keys and the plain text. And we provide guarantees that the isolated data cannot be exfiltrated. But are we done? Do we not have to trust the app now? Can we turn the app stacks to the trusted color? The answer is no, because a malicious application could still spoof the user into thinking that it's using Beeswax when it isn't. And we don't want to have to audit the application. So what a malicious application could do is to lure users into, with promises of heightened privacy, and then kind of pretending they're doing all this end-to-end encryption and then eventually exfiltrating the data. So how can we assure users that the application is using the right API call? So what we do, so a malicious application could do this. It could try to do something where, oh, you can type in here, here's some green locks, some green borders around this box, but all of this is controlled by the application. It's just a false sense of security, so you can't do that. If the application is using the APIs correctly that Beeswax provides to create private areas, well, all of that stuff is managed and isolated in Beeswax. So maybe there's a way where we could add indicators in the page, say, okay, this area is controlled by Beeswax, it's fine. But then again, the application could overlay text or images on top of that and spoof the UI. So we can't do that either. So what we do in Beeswax is that we have a privacy indicator that comes with the extension, and it's displayed in the part of the browser that the applications can't spoof. It's displayed next to the address bar, and there's no way for an application to draw outside its boundaries, and there's no way for pop-ups to fake that area as well. So whenever a user interacts with an area that's been defined or controlled by Beeswax, it will trigger, like this is user keyboard and mouse interaction, it will trigger, flash that indicator icon in the browser, and then the user knows that whatever events are being sent there cannot be exfiltrated by the application. There is no way for the app also to trigger those events because it's not accessible to it. This indicator essentially tells the user that the DOM, the region of interest that it's interacting with, is private. And in that area, the content is hidden from the application. So whatever you type in there, the application can't read. And the events are locked to that region. So back to this slide again. What we've achieved with the privacy indicators, we have the keys in plain text unavailable to the application. And the privacy indicator indicates where events and text by the user goes. So we eventually achieve our goal this way. And so you trust the platform, you trust Beeswax, but the apps don't need to be audited or trusted. Beeswax to fully function has to come as well with key distribution. We didn't want to have to do that out of band. So that's taken care of by Beeswax, the Beeswax extension for the user. And we provide two communication abstractions for the application. The first one is called a friendship channel, which is a signaling channel to pass Beeswax messages between the user's extensions. And the second one is streams that passes data messages. We use elliptic curve cryptography for the friendship channels and symmetric key crypto for the streams. To distribute identities, we rely on a publish-subscribe system, and we use Twitter in our implementation. So basically, when you set up the Beeswax extension, the user will, the extension will generate two key pairs for that user and associate that with the user will specify a Twitter account to associate it with it. And the Beeswax background process will post the keys to the Twitter account of the Beeswax user. And these keys have an expiration. So we have a good practice of reposting these keys every few days. And that gets us around a few Twitter limitations as well with regards to availability of old tweets. And we have, I'm not going to cover it here, but we have a similar process for when you establish friendships with other users. Beeswax background process will fetch keys from other users and monitor them as well if they get revoked. More details on that in the paper. So the friendship channels are bidirectional control channels between pairs of users. So if you have 3 friends, you have 3 friendship channels. And we use those channels to pass invitations. So we communicate keys between users with it. So there's an API call to create friendships that the application will do to talk to another friend. And then streams are the channels on which user messages are being passed. And once you've created friendship channels, you can invite other users to those streams. What the application sees are stream IDs. They're opaque handles to keys. But in the background, the keys are exchanged. So the database and the Beeswax extension will contain keys. Of course, we wanted to see that this was usable and practical. So we experimented with the platform and built 2 applications, one of which is an existing application that we've pimped up to do secure channels. So it's an IRC client for the web. And the second one is built from the ground up, encrypted photo gallery to exchange rich media types. And we evaluated performance as well. So this is very cool. We took an IRC web client, which has a server-side and a client-side component, and we've modified the client-side component. Using 400 lines of code, we managed to add functionality to talk secure with encrypted channels between users, Beeswax users. So you just have 2 Beeswax users, they can quickly go and talk there. It's very easy. And then we also support richer media types than simple text. So we have ways to communicate pictures. And one interesting thing there that was fun to do was that you want to be able to upload files to the Beeswax extension without the application stealing your files. So we had to do something very interesting for a special file chooser for Beeswax. We do JavaScript encryption in the background page, and the cost of encryption is predictable, linear with plain text size, so really no surprises there. We have to instrument the runtime of the page, so there's a 52 milliseconds page load increase for our prototype. And when you interact with the page, the events, we have to do some extra processing to filter out confidential information from events. It's 2.5 times slower to process events, but when you browse, in our experience, it doesn't really, in fact, it's not perceptible. So I talked about just covering the web. And the question is sort of left to future work, but what about mobile? Is there a way to do something similar for mobile? In Android in particular, it'd be great if there was a way for secure modules to be loaded so you can monitor what the application does. And again, if we wanted to port a privacy indicator to mobile, we'd have a way to we'd need a way to reserve parts of the screen to indicate to the user whether or not it's interacting with a private part or not. And this is coming to the conclusion. I've presented Beeswax. It provides protection against exfiltration by application providers. It is a web platform, and like any platform, we can expect that features can be added or removed as the platform matures. It includes key distribution that's built in, easy, automatic, and it's deployable now. What it lets us do in the end is that we can focus scrutiny on the platform, and then every app that uses the platform doesn't need to be audited. And the platform and applications are available on GitHub. Now we'll take your questions.